This podcast is on assessing regression assumptions. We will examine each assumption in turn, discussing their meanings and how to assess whether or not our model meets them. A regression equation is considered to be blue, or the best linear unbiased estimates, if the equation can meet all of the regression assumptions. Lurking off to the side of this slide, Adrien-Marie Legendre, an inventor of regression from the early 19th century, would advise us to take care examining these assumptions, as some are more important than others. And you do not need to worry about the regression equation on the bottom left of this slide. The equation is one I published in my doctoral dissertation, simply to show you what an equation looks like. We will consider a simpler equation in the next slide. Here is the regression model, an equation that we will use to learn about regression assumptions. We will use a bivariate regression as an example to walk our way through the assumptions, since it is the simplest example. As you can see, again, we are speaking of a made-up data set and variables, so we can focus on the analytics. The made-up variables are measured at a single time point, also known as a cross-sectional data set, which will be important for assessing one of our assumptions. To go through our quick interpretation, we first put the table into equation format. We then verbalize the results. Y is explained by the equation 0.4 plus 0.9 times A. The regression line crosses the y-axis when x equals 0.04. If there is a unit increase in the independent variable, then we solve the equation by y equals 0.4 plus 0.9 times 1, or y equals 1.3. The r-squared is 0.80, meaning that 80% of the variation in the dependent variable is explained by the independent variable. Finally, the number of cases in our analysis is 40. This will become really important for one of our other regression assumptions. Here are the regression assumptions for the regression equation y equals a plus b sub 1 times x sub 1 plus e. There are quite a few of them, so we group them into three classes to make their understanding be easier. No specification error, no measurement error, and a series of sub-assumptions that are associated with the error term. Let's pause for a moment. Conceptually speaking, the error term is the e of the equation y equals a plus b sub 1 x sub 1 plus e in a bivariate regression, and y equals a plus b sub 1 x sub 1 plus b sub 2 x sub 2 plus b sub I to n times x sub I to n plus e in a multivariate regression. The no specification error assumption has three sub-assumptions. X and y have a linear relationship to each other. There are no relevant independent variables excluded from the model, and there are no irrelevant independent variables included in the model. The no measurement error assumption is straightforward, while the error term assumption has five sub-assumptions. The error term has zero mean. The error term is homoscedastic, meaning constant error variance. The error term has no autocorrelation, meaning that the errors in estimating consecutive cases are not correlated with each other. The error term has no correlation with the independent variables, and the error term is normally distributed. By the way, you may remember the photo on the side of this slide is of the apple tree which Sir Isaac Newton viewed daily while in quarantine during the mid-1660s when he invented calculus. That was certainly a productive period for him. We start with the assumption of no specification error. First, for regression analysis to work well, there needs to be a linear relationship between the dependent variable and each of the independent variables. Of course, in a bivariate regression, we have just one independent variable. As Lewis Beck and Lewis Beck wrote in their book, quote, numerous real relationships have been found empirically to be essentially linear, close quote. But we should not rely on this statement alone. We can assess the linearity through looking at a scatter plot. We can see that the scatter plot for our regression does indeed look linear. We can also examine the R-squared statistic. If it is pretty high, then we can assume that the relationship is linear, as R-squared is meant to capture linearity to a certain extent. Since the R-squared in our model is 0.80, above the standard for strong models with an R-squared of 0.50, and again, 80% of the variation in the dependent variable is explained by the independent variable, we can conclude that the relationship between the dependent variable and the independent variable is linear, and that that assumption is satisfied. The R-squared plays a major role in the next subassumption of no specification error, that there are no relevant independent variables excluded from the model. The best way to assess this assumption is to check the R-squared for the model. The higher the R-squared, the less likely we will be violating this assumption, because high R-squared values mean that we have few, if any, significant independent variables missing from the model. Since our R-squared is so high, we can conclude that there is a low probability that we have excluded statistically significant independent variables. The picture is of Sewell Wright, the inventor of the R-squared, in a paper published in 1921. The equation he wrote for R-squared is to the right of his picture. He was an agronomist and worked for the Animal Husbandry Unit of the U.S. Department of Agriculture in Washington, D.C. My maternal grandfather, by the way, had a similar job at the USDA. The final subassumption of the no specification error assumption is that there are no irrelevant independent variables included in the model. To assess this assumption, we examine the t-statistics and sigs of the independent variables in the model. The process is straightforward. We note that in this model, the t-statistic is 18 for the independent variable, far beyond the rule of 2, so it is statistically significant. We also see that the sig is 0.001, far beyond the rule of 0.05, so again, the independent variable is statistically significant. Thus, we have no irrelevant independent variables included in the model, and the assumption is satisfied. The photo on this slide is of William Gossett, who invented the t-statistic that we use to test statistical significance. He was a statistician and head experimental brewer at the Guinness Brewing Company about 120 years ago. Gossett developed a way to determine the best yielding varietals of barley using small samples, inventing the t-statistic. Since his work was proprietary to Guinness, he published his work under a pseudonym, Student. Hence, the statistic is known as Student's T. By the way, Idaho is the top barley-producing state in the United States. The next assumption is of no measurement error, or that the dependent and independent variables in the model are measured reliably and validly. We have specific definitions of reliability and validity. We really cannot determine reliability and validity outside of the specific knowledge of the measurement process. So we do not look at the regression analysis itself, but rather at the coding or the code book to see if there are coding inconsistencies in the notes. In IBM SPSS for statistics, we can find the code book in the variable view mode once we have our data set open. For now, we can assume that if a data set is reputable and used frequently in the social sciences, then we can consider this assumption to be satisfied. The error term has zero mean is our next assumption to consider. It is a minor assumption and only concerns whether or not the y-intercept is normally distributed. Since we focus on the statistical significance of the independent variables, and of the model more generally, we pretty much ignore this assumption. By the way, one of our greatest statisticians is a woman who is normally known for something else, Florence Nightingale, the 19th century British nurse who served in war zones. She charted mortality rates there and compiled data sets of factors that influence mortality. Her hand-drawn charts were well known and changed the way the hospitalization proceeded in the Western world. One of those charts is on this slide. A really important assumption is that the error term has constant error variance. This is called homoscedasticity, which comes from the Greek words homo, or same, and skedanumi, or scatter. The reason that this is so important is because if we do not observe constant error variance across all values of the independent variable, then we cannot trust a single slope coefficient to represent the true effect of the independent variable on the dependent variable for all values of the independent variable. Instead, the independent variable will have different effects on the dependent variable based on the values of the independent variable. Instead, we need a consistent slope coefficient, which can be applied to all values of the independent variable without bias. To assess homoscedasticity, we need to examine a special scatter plot called a residual plot. It is at the bottom of this slide. A residual is the error in the predicted value of the dependent variable for each case. It is represented by the equation r equals O minus p, or the observed value for the dependent variable, the O, minus the predicted value of the dependent variable from the regression equation, or p. Once we calculate these residuals for each case, we can plot them in a scatter plot where the y-axis contains all the possible values for the independent variable. The x-axis contains all the possible values for the independent variable, and the y-axis contains the residual values, standardized by their z-scores so that they are constrained between +3 and -3 standard deviation units from the mean residual value of 0. As you can see from the scatter plot on the slide, if we trace our eyes from left to right across the plot, we can see that the band of points is relatively constant. This indicates homoscedasticity. If there were a pattern of points from bottom left to top right, then that would tell us that for small values of the independent variable, there would be an overprediction of the dependent variable. And for large values of the independent variable, there would be an underprediction of the dependent variable. This would be systematic, meaning that it is very likely to occur, and it is a chronic error, meaning that it would need to be fixed. The tools used to fix it are beyond the scope of this course. I should add, though, that in this case, because we see constant error variance, that this regression assumption for our model is satisfied. Our next assumption is that the error term has no autocorrelation, which means that the errors in prediction, the residuals, in consecutive cases are connected to each other, or highly correlated. When this occurs, the standard errors in predicting the values of the dependent variable are artificially reduced, and thus the t-statistics are biased toward rejecting the null hypothesis, when in fact we should accept the null hypothesis. This is called type 1 error, or an overconfidence in rejecting the null hypothesis. Technically, we can diagnose autocorrelation through using the Durbin-Watson test. James Durbin and Geoffrey Watson are pictured at the bottom right of the screen. They were British and Australian statisticians, respectively, during the mid to late 20th century, and jointly invented this test. However, we can circumvent the test by asking a simple question. Is our data set cross-sectional or time series? A cross-sectional data set is measured at one time point, whereas a time series data set is measured over repeated time points. The data sets that we use in this course are cross-sectional, measured only over one time frame. The cross-sectional data sets are extremely unlikely to have autocorrelation, whereas the time series data sets are extremely likely to have autocorrelation. We can see why this is true. The consecutive cases in cross-sectional data sets are unlikely to have any special connection to each other. For instance, in the data set of the US states, the normal order of the states is alphabetical. It is hard to see the connection between Alabama and Alaska, consecutive cases, as well as between Idaho and Illinois, and between Nevada and New Hampshire. Thus, errors in predicting Alabama and Alaska do not seem inherently connected. The same goes for Idaho and Illinois, and Nevada and New Hampshire. In contrast, the consecutive cases in time series data sets are often years, or quarters, and there would be a very close connection between those cases. For instance, GDP per capita in 1970 is very close to the GDP per capita in 1971, which is very close to the GDP per capita in 1972, and so on. Thus, errors in predicting GDP per capita are closely aligned. All we need to do with the autocorrelation assumption, then, is ask ourselves, is our data set cross-sectional or time series? If it is cross-sectional, then we do not need to concern ourselves with this assumption. It's satisfied. If it is time series, we then use the Durbin-Watson test to determine the extent of the autocorrelation. Since the data set that we are using in this hypothetical case is a cross-sectional data set, we can just simply say that because the data set is cross-sectional, we have satisfied this autocorrelation assumption. Or I should say, no autocorrelation assumption. We have two more assumptions to consider. First, the error term should not be correlated with the independent variables. We can think of this as a corollary to one of the earlier assumptions, that there are no relevant independent variables excluded from the model. Further, let's consider the error term as a collection of potential independent variables that could be included in the model, but aren't included for whatever reason. If we include as many relevant independent variables in the model as possible, then we reduce the number of those variables in the error term, and thus the likelihood that the error term is correlated with the independent variables in the model is relatively low. Recall that for our purposes, relevant means statistically significant, and irrelevant means statistically insignificant. Thus, we need to examine the R-squared statistic to determine the number of relevant independent variables in the model. The higher the R-squared, the greater the confidence that we have that the relevant independent variables are included in the model, and the less likely it is that we're violating the assumption. Since R-squared is 0.80, we are less likely to be violating this assumption with our hypothetical model. The photo on the lower right of the slide is of a plaque that the Irish Statistical Association and Dun Laoghaire Rathdown County Council erected at the site of William Gossett's home in Dublin, in order to honor Gossett's contribution to good inferential statistics and good beer. You can practice reading Gaelic on the top half of the plaque. Our final assumption is that the error term is normally distributed. This assumption is also a bit downgraded for us because we can assume a normal distribution given a large enough sample size. This is called the central limit theorem, and states that if the sample size is at least 30, then we can assume that the sample is distributed normally. Thus, all we have to ask is whether or not our sample size is large enough. Frequently, in social science, our sample sizes are quite large. The 50 US states, the nearly 200 countries around the world, the approximately 1,500 cases in large-scale surveys of the public. Those are examples of larger samples. And if our sample is large enough, then we can say we satisfy this assumption. Since our sample size in this example is 40, we can invoke the central limit theorem, invented by the French mathematician Pierre-Simon Laplace in the early 19th century. His picture is on the left at the bottom of the slide, and say that our sample size is sufficient to satisfy the normality of the error term assumption. We also have to thank, for this solution, the person in the far right photo on this slide for developing the empirical rule that governs interpretation of the normal distribution, Afnuty Chebyshev, the 19th century Russian mathematician. Thus, we have satisfied all of the regression assumptions and sub-assumptions for our hypothetical model. After all of that, you could probably use some Zen meditation. Here's a photo of Skytop Tower at Lake Mohonk, New York, near to where I grew up. The mountain is only 1,500 feet high, but the valley floor is at sea level, so you can see across the Hudson Valley and back into the Shawangunk mountain range from the tower. You should visit it sometime. For now, enjoy the view from the town of New Paltz, and thank you for listening to this podcast.